So in the last video, we took a look at this definition of how we could come up with an idea for how to compute the work as I move an object in a straight line from A to B. And what we saw is that we needed to have a function that defined the force acting on the object at any given time. Now, this is actually one of many different possible ways that we could try to think about the amount of work that is going to be computed. I'm going to actually go ahead and deal with this in a slightly different way. What I'm going to do is to actually rethink this construction slightly. I'm going to, instead of dealing with f as a function that quantifies the amount of force acting on the object, I'm instead going to try to imagine little amounts of work that are going to be adding up to our total amount of work. That is, I'm going to go back to this representation of these rectangles and try to imagine if I can find the actual amount of work that's going to be done on every given increment of the problem that is in question. To kind of see what I mean by this, let's take a look at example number 1. So suppose I have the following. A 200-pound cable is 100 feet long and hangs vertically from the top of a tall building. You know, like cables do. Gotta love word problems. Okay, so how much work is required to lift the cable to the top of the building? Now, of course, with this, it might be helpful to try to go ahead and draw a quick picture. You'll see here that I'm going to start by drawing maybe a nice little building over here. Please don't be intimidated by my artwork. I have years of experience. Let's see, obviously a building would make sense if it had had some doors, maybe some windows here. You know, this is a good time. Great, fantastic. And if there's going to be a cable that's at the top of this tall building, and I'm interested in the amount of work that's going to be required to lift the cable to the top, let's suppose I have like a little person standing on the top of the building. It's either a very short building or a very tall person. And we're going to go ahead and imagine that the cable is maybe going to stretch like this. Okay, so this is it. This is the cable right here. We're going to imagine this person's going to reach out and grab that cable. Okay, so if I have this sort of scenario, I can see here that one of the first things I might be able to do is to start to get some numbers here in the picture. If I know the cable is 100 feet long, one of the most important things that I can start to do is to label or kind of position a number line here in the picture. I want to go ahead and label some numbers on either side of this number line, so this cable is going to be 100 feet long. Now, there's many ways to do this, and I'll just show a couple. Obviously, I might be able to go ahead and mark my number line with the following values. Maybe I put 0 at the bottom and 100 at the top. The cable's clearly 100 feet long. Notice I could easily reverse this by putting 0 at the top and 100 at the bottom. But there's actually a ton of different ways that we could do this. I could put 50 at the top and negative 50 at the bottom. And in fact, it doesn't matter at all how you label the number line, as long as it corresponds or measures out this 100 total feet. Now, in my notes, I take two different approaches, one where I put 100 at the top and one where I put 100 at the bottom. I'm going to start here by putting 0 at the top and 100 at the bottom. I'm just going to choose to operate this way. Now, if I have this, I'm going to go ahead and start to think about kind of what we did in that opening exploration. I'm going to imagine that I could take my cable and chop it up into a bunch of smaller pieces. And instead of finding the amount of work to lift the whole cable, I'm going to try to go ahead and figure out how much work does it take to move just one section of cable. So let's suppose, for the sake of argument, that I'm going to focus on this little section of cable right here. Now, I'm going to have to go ahead and measure a couple things about that cable. I'm going to probably have to measure how much force I need to apply to that cable to get it to move, and ultimately how far I need to move that cable. So I'm going to go ahead and start by trying to figure out how much force I'm going to need to move that one single piece of cable. And so I'll start up here by just writing that I'm working with a single piece of cable. This is an important distinction, because later we'll talk then about how we summarize this to get the whole cable. All right, so for this single piece of cable, I might notice that I don't really know how long it is. If I divvied up my cable into equal pieces, the best I could really say is that this is delta x feet long, right? Notice I am measuring in feet here. So if this is delta x feet long, I, I don't really know how much it's actually going to weigh. Now, I know that the entire cable weighs 200 pounds, and so maybe I could start by determining this. We know that the cable weighs 200 pounds spread over a distance of 100 feet. And so, of course, that would simplify down to 2 pounds per foot. So if my cable weighs 2 pounds per foot, and my piece of cable here is delta x feet long, I can say that our piece weighs 2 pounds per foot times delta x feet. If I track what's happening here with the units, I can see that I'm going to be left with just a number of pounds. That cable weighs 2 delta x pounds. Okay, so that's really good, because what I'll notice is that since I'm working again in the English system, remember that pounds is a measure of force. So I already have the force that I need to calculate my work. The last thing I'm going to need before I can grab the work to move this piece is the distance that this piece has to move. So how far does this piece have to move to get up to the top? Well, it's kind of hard to say, because like this top portion up here, this very top tick mark, doesn't really have to move as far as that bottom tick mark. So instead, what I'm going to do here is I'm going to go ahead and introduce a small piece in here that I'm going to call my delta xi, or sorry, my xi star. That's going to kind of serve as a representative height over here on my number line for kind of where that piece of cable actually is. So notice if I said that this entire cable was resting at height xi star, how far do I have to move it to get it to the top? Well, you might notice again that we're back to measuring lengths of line segments. How far is it to go from here back to the top? Well, that would just be xi star minus 0, right? That's the length, or that's a total of just xi star, and if I put units on that, that would be units of feet. So now that I have the force and the distance, I can easily go ahead and calculate the work. My work is going to be 2 delta x pounds times xi star feet. Or I could write this as 2xi star delta x foot-pounds. Now that's the amount of work, again, required to move one single piece of cable. And now I can try to summarize that for what would happen when I look at the entire cable. If I look at the entire cable, I can easily see that what I would want to do is to say that the total amount of work is going to be adding up all of, I should shift this over a little bit, but it's going to be adding up all of the amount of work for all the individual pieces. So starting at piece 1 and going to piece n, I would want to add up 2 delta xi star delta x foot-pounds, and I want to add that for all the different pieces of the chain. But then, of course, I want to go ahead and take a limit as the number of pieces approaches infinity. What this then means is I can transform this into an integral. Notice that the function in there is going to be 2x delta x, which will then get transformed into dx. Let me go ahead and rewrite that just so it's a bit clearer. So I have a 2x dx. Now the bounds are going to stand for the same thing that the bounds have always stood for in all of Chapter 2 thus far, which is where are the pieces of the cable? Just like we asked where were the rectangles starting and stopping, or where were the washers existing? Where did the shells start and stop? Where did our line segments begin and end? We have the same idea here. And notice that we're going to have little bits of chain that we need to move from 0 all the way to 100. Notice this is even an unbelievably easy integral to calculate, because it's just going to be x squared evaluated from 0 to 100, and 100 squared is just going to be 10,000. And notice I can put my units on there. That's 10,000 foot-pounds. So this is actually a really easy sort of a question to do, but I have to understand how I get each of these individual components. Again, it wouldn't have mattered if I would have switched around these blue values, and again in my notes I do show what it would look like if I started with 100 on top and 0 on the bottom. I'm never going to care how you label your picture, and regardless of how you label it, you should always end up with the exact same answer that I did. Now let's take a look really quickly down here at this kind of extension, this extra question. What if it was the case that there was a 500-pound trough of water that was attached to the end of the cable that's also going to be lifted? Okay, so I don't know, just imagine, that I get something that looks like this, right? So I have now a big trough of water. It's going to get added on here, okay? So there's a big trough down there, here's water, water's blue, and that's also going to get pulled to the top. Well, when I deal with objects attached at the end of a chain, it's often customary to think of those objects as just one single piece that's moving all at once. And so it ultimately becomes very easy to answer this question. So here, to find the total amount of work, I would ultimately need to find the work from the cable and kind of just add on the work from the trough. So if I can find those two things separately, I'm good to go. Now, of course, from up above, we already saw that the work from the cable was 10,000 foot-pounds, so nothing there is really different. But when I deal with the work for the trough, I can just keep in mind that I can always calculate work by knowing force times distance. So I can ask myself two questions. First, how far am I going to have to move that trough to get it to the top of the building? Well, if it's at the end of the chain, it's got to move 100 feet. So I automatically have my distance. How much force am I going to need in order to push or pull on that object to get it to move? And well, if the object weighs 500 pounds, which is a measure of force, I would need to push or pull on it with 500 pounds to get it to move. And so I can see here that my force is going to be 500 pounds multiplied over the distance of 100 feet. And so I end up with 10,000 foot-pounds of work for the cable, but I end up with 50,000 foot-pounds of work for the trough. And so, of course, that gives me a grand total of 60,000 foot-pounds of work. So hopefully you can see here that by adding something to the end, whether it's a trough or a box or a crate or some other object, it doesn't really change ultimately how I do this sort of a calculation.